So I'd like to thank the organizers for inviting me to give this talk. I'm going to be talking about enabling performance portable climate simulations on Aurora and Frontier. I have to make a couple of disclaimers. I'm actually pretty new to the project. I've only been with the project for 1 year. And even though I'll be talking about climate simulations, I'm actually not a climate scientist at all. I'm actually a condensed matter theorist. But I am a computational scientist, so I'll be talking about an overview of E3SM, a little bit about some of the challenges that we face with GPU programming, and about the general concept of performance portability and what we're trying to do to achieve this, and then just some of our outcomes. This interesting photo, it says here Chicago metropolitan area, but this is actually, those of us from the Chicago area, this is actually closer to Rockford, which is not really the Chicago metropolitan area in my opinion, but this is this ominous cloud. It's a convective storm system, and one of the scientific goals in climate modeling is to actually correctly capture these type of cloud phenomena without in a way that our simulations can scale to basically 100 simulated years in a practical manner. So a little bit about E3SM. E3SM is we're the DOE climate code. It's a global Earth system model. It couples atmosphere, land, ocean, and ice components. We're a very large collaboration. On the project, on the ECP project, we have 8 of the DOE labs, number of university subcontracts. We're kind of spread over 53 FTEs, 87 individuals, because some of us are just part-time. I should say this includes both the big ECP project and another project that we're also funded by BER. And our climate code is driven by some of the Office of Science mission interests, understanding energy and water issues looking 40 years from now. And one of our key computational goals is to run well on the DOE pre-Exascale systems, for example, Summit and Perlmutter, and on the upcoming Exascale systems, Aurora and Frontier. This is our URL. We have some nice videos, interesting videos on the DOE Science YouTube channel. I didn't know we had DOE had a science YouTube channel, but we do. This is what a climate simulation is in a nutshell, and I hope to build upon some of the ideas that Thomas and both Andrew and Doug touched upon earlier. Basically, our grid, we're trying to simulate the whole Earth, the processes going on in the atmosphere, water, and land. And sometimes this is called a 2.5 dimensional grid. They're basically the horizontal grid around the globe, and the vertical grid that's basically pretty thin in the direction of the atmosphere. And what's called the die-core, this is basically just solving CFD using a finite element basis. And then there are also we model a number of physical processes. This might be too small to see, but we're trying to model precipitation, advection in the air or in the water, melting. And this is done with various different numerical methods, including finite difference methods. So one of the largest sources of uncertainty in these climate simulations is how we handle the clouds. Are we capturing convection convection in clouds accurately. So the more accurately we can capture this, the better fidelity our simulations would have. So this is a major challenge for us. And there are two approaches you can take to dealing with clouds and convection. So right now we do have something called, you'll see it in E3SM, there are a lot of interesting acronyms. So our simple cloud resolving atmospheric model is just called SCREAM. And this has been rewritten in C++. So E3SM is mostly Fortran, but this has been recently rewritten in terms of C++ and Cocoa. So it does work on GPUs, and it will scale to resolutions that we're looking for to resolve convection in clouds up down to the 3 kilometers. The one big problem is this is just simply too computationally expensive. For those of you who are familiar with Insight, which is the big DOE allocation program that gets a project access to resources like Aurora and Frontier and currently Theta and Summit, with the entire allocation, we can only simulate 10 years. Not only do we want to simulate order of magnitude up to 100 years, we want to do many different simulations with varying parameters and models, etc. So while SCREAM is available in E3SM, the other approach that we're developing, you'll hear in my talk, it's called MMF. It's a multi-scale modeling approach. It's been dubbed super parameterization. You'll hear me refer in the talk. I'll switch back from either using the term MMF or super parameterization or CRM, cloud resolving model. But I'm basically referring to this MMF model. The algorithm is it's very computationally intensive. It's also very ideal for GPUs. The big difference between these two is in here there's simply too many degrees of freedom, and the time steps you can take are limited. You can't take very big time steps, and this is where the heart of this MMF approach is. You kind of reduce the degrees of freedom, reduce them to those that are absolutely necessary, and you're able to take larger time steps. So our Exascale challenge problem, again, is to resolve all of these processes. Cloud resolve the clouds, resolve the eddies in ocean and ice, and you'll remember Thomas talked about our throughput. We want to be able to simulate, do 5 simulation years per day. And we want to do this for 100-year simulations, but we also want to do many ensembles. So you could think of it of an uncertainty quantification by another name. All right. I won't get too much into what MMF is, but it's probably similar to other multi-scale modeling approaches that you might be familiar with in your domain. There's too many degrees of freedom, so you kind of extract broader ones that actually make the largest impact, and use that to do your simulation instead. GPU. Scientific computing with GPU is going to be ubiquitous in DOE. In 2020, Perlmutter is coming online. This is the machine at NERSC. It's going to be NVIDIA GPUs. Aurora is going to be Intel GPUs. All Frontier AMD GPUs. So those of us who've kind of punted on trying to get our codes working on GPUs, we can't really continue to punt. and we just have to go ahead and get our code running on GPUs. I'll mention that we do have dedicated CPU resources that are paid by BER. We have here at Argonne a Skylake system called Anvil, which is part of the LCRC resource. And for your amusement, we have a machine. I thought I mentioned this. We have a machine at PNNL. It actually is called Copy McNodeface. And my joke is, when you let technical staff vote on the name of a computer, this is what happened. You end up with a computer called Copy McNodeface. The host login's name is actually Compy, because that's way too much to type for logging in all the time. And we do get a lot of science done on these machines. So this is just my own commentary on maybe why GPU programming is so hard. So SIMD programming, it's been around in modern HPC for a while, and I think we've just actually gotten really good at it. Some domains more than others. In the other domain I work with, electronic structure, my joke is we, some of our codes may someday replace LIMPAC as a benchmark because they find new and clever ways to use complex matrix multiplies. And also with SIMD programming, at least as implemented in modern CPUs, we also been able to make use of all this extra hardware that's on there to handle branch mispredictions and reordering instructions, and these are not present on the GPU, though some of that some of that will change. With GPU, just essentially SIMT programming, which is kind of a merger of SPMD and optionally SIMD programming, we have to think a lot harder about how do we expose more data parallelism. So some of the changes we've made in our code is, so usually we require threading higher up in a loop or even higher up in the call stack. And then because we have to hide the latency for memory transfers between host and device, we even have to build in even extra concurrency to hide that latency. And we're still working on doing that. Then the other things, such as managing two memory spaces between the CPU and the GPU. Programming models have reduced the amount of effort, mental effort to do this, and programming effort to do this. And also there's some operations that just involve the CPU no matter what. For example, MPI, though even that's also improving, so more of MPI now occurs on the GPU itself. So I think the point I want to drive home is that our current CPU algorithms will most likely not be good GPU algorithms. However, one thing that I've seen from one of the other ECP projects that I work on is if you do come up with a very efficient GPU algorithm, you might find that it will work well on the CPU too, because you will have minimized branching, you will identify more places to express data parallelism, and you can express this in OpenMP for CPUs. You can express this extra data parallelism either as longer SIMD vector lengths, or maybe nested OpenMP or OpenMP tests. So it's not wasted effort. You can leverage it for CPU code, and then also you have to think a little bit more about MPI communication, how to minimize it, how to amortize it, maybe do things with active messages, where you're rather sending a task rather than sending the data. So our performance portability strategy. So our job is a lot easier now than it was many years ago. We have, as Doug mentioned in his talk, we have from the software tech part of ECP, we have Cocos and Raja. Those programming models are limited to C++. Our code is Fortran, but it saves us from having to think too hard about whether are we going to need to use CUDA, are we going to need to use HIP, SYCL, DPC++, or something else. It sort of hides that extra level of pain for us. These programming models are nice, and then they have multiple backends, and at least one will work on these machines, hopefully more than one. And then I will also say that OpenACC, which we have a lot of OpenACC code in E3SM, has also reduced the barrier for using GPUs. So instead of writing CUDA, we can write OpenACC in a very similar manner to OpenMP code that many of you are familiar with. The other nice thing about OpenACC is that I should probably have put, this is not, I should say, probably use the word descriptive, not prescriptive. A lot of the ideas in OpenACC, a lot of the directives have influenced the development of OpenMP 5.0. One of them is this loop directive that rather than the application developer saying parallelize the loop in this particular way, you kind of hand off that parallelization effort to the compiler, and it chooses the right combination of parallelism to express with OpenMP5. I think unified memory is going to help us a lot, even if it's whether it may not get us the performance we want, but it will actually ease development, so you don't have to worry about whether an array is whether you copy the array back to the CPU and whether it's been modified or not. And then for getting for squeezing out extra performance, OpenMP5 will have meta directives, and we can declare variants. So if we have to create a loop that's very specialized for a particular architecture, we can kind of obfuscate that a little bit in the code. So our plan is some components will use C++ and Cocos. Right now we have a lot of Fortran and OpenACC. We will migrate that over to OpenMP 5.0 by the time these machines come in. It's going to require a lot of early access to compilers and a lot of testing. One tool that I'll mention to the audience, actually it's a tool that I wrote. We have a Python-based converter to translate OpenACC into OpenMP. And this is a source-to-source translator. It's just about a couple of hundred lines of Python code to translate OpenACC to OpenMP. And this is just to kind of reduce the barrier to adoption to OpenMP, because we do have a lot of OpenACC code right now. And then just a general comment, I think the best performance portability strategy is really a well-designed code with modern programming practices, leveraging libraries. We're now using Git, CMake. We used to have multiple scripting languages like Perl, Python, and can't remember what the, maybe Bash, and we're moving everything to Python. We also created a, excuse me, a thin I/O portability layer, which I'll talk about. This is the successor to PIO, the Parallel I/O library. This is the E3SM version. It got recently renamed the Scorpio, again with the interesting acronyms that we use in this project. I think it stands for just scalable PIO. Since I'm running out of time, so the basic idea is we will, on the back end, we can have, before we used to use NetCDF and PNetCDF and optionally HDF5, we redesigned PIO so we can put accommodate other backends, so we can accommodate, now we're accommodating audio, so I'll show you some results about that. And then we have a Fortran and C API. And then it uses techniques like aggregation and compression to speed up I/O. I'll just show you some results because I'm running out of time here. We ran 2 cases here, and the G case has more data, more resolution, and you can see here, this is what we were getting with an earlier version of PIO. This is both with PNet CDF. This is what we're getting with Adios at NERSC. This is again PNet CDF versus Adios. This is gigabytes per second, the throughput here. This is on Summit, running on 96,000 MPI processes. So some highlights. We ported the CRM over. We had to basically rewrite 20,000 lines of code using Fortran and OpenACC. This is a huge fraction of the cost of running the MMF. It's like we've documented it in a CAR report. I think these CAR reports are, I think they're publicly available, and also in an ECP milestone report. We did have a Gordon Bell submission. As you can see, we really get only a small percentage of peak, 2.5% of peak. The code is, for the most part, very memory bandwidth limited. So this is why we get such a small percentage of peak. And we're already achieving, we're able to achieve 1.8 simulated years per day. In the couple of minutes that I have left, I want to show you some results. So again, the metric that's of interest to the scientists is simulated years per day. We're interested in maximizing that. We often will run our simulations at the strong scaling limit, where we're starting to run out of work per node. And what you see here, this is number of elements that are being evaluated in a time step. So here, more elements is better. And we have several generations of Intel processors: Ivy Ridge, KNL, Skylake, Haswell. We often end up running our simulations in the strong scaling limit, which is all the way out here. And you can see we actually get quite a bit of throughput on a Skylake machine. The GPU, if you have big enough workload, you can see that we could get the throughput out on it. But we're often working in this regime for our simulations. The other thing I'll point out is that even over many generations of multi-core processors, and to some extent GPUs, here at the strong scaling limit, we've only gotten a factor of 2x in speed up. I think again, this is because many of our kernels are memory bandwidth limited. All right, but it is possible to achieve. I don't want to be the prophet of doom here. We are able to achieve significant gains in GPUs, but only out here in the high workload per GPU regime. So the MMF algorithm is very appropriate for GPUs. It runs well. We're up and running. These are results from Summit. This red line here is results from Summit. You can also see the result from Corey here. I think we've probably left some performance on the table. We should be hoping to get much more than just 2 or 3x from these GPUs. Hopefully, we can get maybe an order of magnitude, and there's still time to work on this. I want to make a plug for a meeting that I'm I and some people at Argonne are co-organizing. There is a DOE Performance, Portability, and Productivity meeting. It is going to be in April of 2020 in Kansas City, Missouri. This is a picture of Kansas City, Missouri. I can't promise you it will look this nice in April, but this is the first photo that came up on Google. If you want to learn more about this meeting, you could subscribe to HPC P3 Announce, or you could just send me an email, and I could subscribe you to the mailing list. All right, some acknowledgements. I borrowed many slides from Mark Taylor and the rest of the 3SM team, and then Doug and Barb for giving us the money to carry on this work. Thank you very much. Thank you.